Okay, let's get started on chapter 6, and today we're going to cover integer programming and specifically binary choice models. Integer programs are, I call them linear-ish programs. Actually, restricting your decision variables to be an integer is actually a violation of the rules for linear programs, but we get around it, and so we are still able to use the linear solver. But anyway, it's where some or all of the decision variables are required to be integers. Okay, and we can envision a circumstance where we might have a nonlinear program or a nonlinear problem that requires integers as the variables, but actually they're very difficult to optimize and really beyond the capabilities of solver. So, some linear programs, like the special network models that we talked about, they produce integer results even when you don't require them. Okay. Other programs that would seem to require integer results, like the Brown Furniture one, are just for planning purposes. And so when we get 5.9 tables or 20.6 chairs, that's fine. So some of the programs that we've already done have been, you might have looked at them and said, well, that doesn't really make sense. These should be integers. But for planning purposes, we simply accept the non-integer results. Or you might run it without an integer requirement and round the results up or down. Okay, so any of those are ways of getting around an integer requirement without actually requiring integers in the decision variable fields. So there are three types of integer programming models. Okay, the first is where some or all of the decision variables have to be integers. Okay, there is a model where some or all of the decision variables are yes or no types, and those are our binary variables, and we will typically use one or a zero in those cases. And in fact, when you there is a constraint specifically in solver for binary, and it produces a one or a zero. There are also models with logical constraints, and we use these with binary variables. So, for example, if we want to expand or make certain products, if we choose to expand, we can make certain products. If we choose not to expand, we must purchase the products. So, at some point in the model solution, we end up with a yes or no question, and if we answer yes, we go off in one direction. If we answer no, we go off in another direction, and we'll get to all of those. So let's take a look at a company called Callum Communications. All right, all the employees work 5 days on and 2 days off, and working weekends gets the workers a premium salary. And they get $440 for one weekend day and $470 for 2 weekend days. Okay, and so here is our the days of the week and the requirements that we have for workers on each of those days. So without the integer requirement, we simply lay this out like a staff scheduling problem. Okay, and so we've done this kind of thing before. It's not that difficult. And we lay it out so that our costs are down here, and we would multiply to get our objective. We would multiply our costs times the number of staff. But as you can see, we have fractional results in the staff fields. Okay, and we know that that's not going to work. So keep in mind, take a look at our objective total. It's 86, 56, 67. All right, because I said before that we can take a different route with this. All right, we could round these up or down. All right, and that certainly is a legitimate way of doing things. But follow along here, and we'll see what happens. So let's compare them. Without the integer requirement, we have, as I said, fractional solutions, and we have an objective of 86, 56, 67. If we simply round them up, okay, 3.6 goes to 4, 1.6 goes to 2, 2.6 goes to 3, and 0.67 goes to 1. All right. We end up with an objective of 9260. All right. And of course, it makes sense that it's gone up because we have more people working, even if they're fractional people. All right. Now, what if we rerun the program and require the solution to be an integer? Okay. We get actually there are two different optimal solutions. They both produce 8790, okay, as the objective. Now notice that it is still higher than without the integer requirement. That makes sense, right? Because whenever you add a constraint, your objective will get worse, okay? But it is better than simply if we round, okay? We get a slightly different solution, a little different mix of people and days, all right? But they are both better than simply rounding. Okay, so as you can see, dealing with an integer requirement by rounding is not necessarily the right thing to do. And so we end up putting the integer requirement in solver. So this is the options dialog box for solver. Okay, and so there are some things that we need to consider, especially when we are doing integer programming. Automatic scaling, okay, by default is checked. And this allows solver to, there are sometimes when there are parameters in the model that are scaled very, very differently. You might have some values in the millions, and then you might have some values out to 15 decimal places, okay? And that can cause solver some problems. So if you check automatic scaling, solver will actually attempt to deal with that for you, all right? And actually unchecking it and checking it can produce slightly different results in some cases. The one I really want to focus on is the integer optimality percentage. All right. Now, by default, this is set to 1. Okay. And what that means is that solver will stop looking for a solution when it is within 1% of the true optimal solution. All right. If you keep it set to 0, some models will require a very long time to solve. Okay. If you're having trouble finding an optimal solution, you might start higher, say like at 5%, and then work down if you can. All right. But this is the default is 1, and typically that is sufficient. Although I think for the problems that we're going to do, for the most part, even 0 is okay. Okay, so the preceding examples use the same basic process as other linear models. Okay, so other than requiring the integer constraint, they look the same as the models that we have been doing. Okay, and so we've had pure integer problems like the staff scheduling. We can also do mixed integer problems where some of the decision variables need to be integers, but all do not. Okay. The differences between the linear models that require an integer and the linear models that do not is resolved within solver. Okay, not really within the model itself. All right, and as we saw, an integer solution isn't necessarily the same as a rounded non-integer solution. So if you round up or down, that isn't going to give you the same optimum as if you required integers in solver. So let's take a look at binary choice. Okay, this is where one or more of the decision variables not only have to be integer, but they can only be 0 or 1. So let's take a look at the Newton Corporation. They have reserved $40 million for capital projects. There are 5 projects to choose from, and the goal is to maximize the net present value. So for data, we have the 5 projects, the NPV for each of them, the capital expense for each of them, and the budget, which is $40 million. Okay. And so in the decision fields for project 1 through 5, we will simply put a 1 for yes and a 2 for no. Okay. And our objective is to maximize our total net present value. Our constraints are the expenditures times the projects has got to be less than or equal to $40 million. All right. So how would you do this by hand? All right. You would probably start putting in, you might start with the project that has the highest net present value and just go down in the line. All right. But then you're going to end up dealing with remainders, and this is one that actually could be fairly easily done by hand, but it's simple for demonstration purposes. Okay, so the Newton Corporation. If we do a simple linear program without integer constraints, we end up with 5 in the P4 slot, all right? And our net present value is 8. Of course, that doesn't make sense, right? We can't do the same project 5 times. So we have to constrain, let's constrain them to be less than or equal to 1, all right? So then we get another solution, but we have a fractional result, okay, in P3. We can't do 2/10 of a project either. So what we do is we set the constraints to be binary, all right? Ones or zeros, and then what we end up with is P1, P3, and P4 with a maximum net present value of 6.8, okay? It's not as ideal as the linear program, but the linear program is not feasible. Neither is the program that sets the variables less than or equal to 1. We have to use a binary constraint. All right, let's take a look at another integer programming model, and that is the set covering model. Okay, set covering is the binary choice version of the covering model, all right, that we've already talked about. It's where we want to minimize our objective, usually cost, using greater than constraints, okay? And it involves the selection of objects to meet our coverage requirements, just like the simple covering model, all right? But where the selection is a binary choice, okay? So each column in the constraint represents a choice and the coverage or the set that it provides, all right? So let's take a look at the Metropolitan Police Department. All right. This is a grid of the area that they have to cover. These are police patrols. All right. The requirement is there must be one patrol in a sector or in an adjacent sector. So, for example, if there was a patrol in Sector 1, that would cover Sector 2, 9, 10, and 11. Okay. So, whereas if there was a patrol in Sector 14, it would cover 14 and 12, 13, 7, and 15. Anything that is adjacent. However, there are two sectors that are not adjacent. There are apparently buildings there, or really no way to pass from 14 to 7 and vice versa, or 13 to 9. Okay, so they are not adjacent. So we have to keep that into consideration. And so the question becomes, how can we provide coverage for this area with the minimum number of patrols? Patrols cost money, okay? So we need to provide coverage. We need to minimize the number of patrols, and we have to keep in mind that there are two regions that seem to be adjacent on the map but aren't really. So we'll have to keep that in mind. So we create what is known as an adjacency array. Okay, this takes a little bit of work. All right, but we lay out a 15. There are 15 regions, right? So we lay out a 15 by 15 grid in Excel, and we put a 1 wherever there are adjacencies. So we know, for example, that 1 is going to be adjacent to 1, right? 1 is also adjacent to 2. All right, it's adjacent. So 1 is adjacent to 1. It's also adjacent to 2. It's adjacent to 9, 10, and 11, right? We go down to region 2. It's adjacent to 1 itself, 3, and 9, and so on. And so you build this adjacency array, and this is going to essentially be your constraint matrix. Okay, so here is the spreadsheet model. All right. These are at the top we have the sectors 1 through 15. And then the decision variables is simply a question. Do we locate a patrol in this section? Yes or no, 1 or 0. All right. The objective is to minimize the number of patrols. Okay. And so in the adjacency array, all right, our left-hand side indicates that the solution, the sum product of the row times the number of decision variables has to be greater than or equal to 1. What that means is every single region has to have a patrol that is adjacent to it if it's not specifically in it. Okay? So, for example, we do not, as you can see from the solution here, we do not have a patrol in region 2. Okay? But we have a patrol in region 1, which is adjacent to region 2. So, the sum product works out. Okay? Take a look at this, work it out in your mind, work backwards if you have to, but understand how this works. All right? Set packing is another type of integer program. All right? It's a binary version of the allocation model, which is where we maximize our objective using less than constraints. Okay? And so it involves a selection of sets that avoid possible conflicts. And so each column in the constraints represents a set and potential conflicts. All right, so let's take a look. So let's take a look at set packing with an example from National Software House. Okay, NSH is seller of educational software, and they are looking at targeting colleges in 11 different regions. Okay, they have 3 sales representatives, and each rep can be active in one region and one adjacent region. All right, so they will be looking at pairs of regions. Only one sales rep is allowed per region, so we don't want them to overlap. Okay, and the goal is to maximize the number of students reached. So here's the map. Okay, so there's 11 regions, and so for example, region 1 there's 68,000 students. All right, region 2 there are 48,000 students, and so on. So how is this going to look in our spreadsheet model? And you really need to start thinking about what are the questions that you have to ask? What are the possible solutions? And that helps you build the spreadsheet model. Okay, so the model is laid out here. We have 11 regions and we have the population there at the top. And then we have the number of pairs, okay? And then you start plugging in essentially the absolute number of possible pairs of regions, okay? And it turns out that between the 11 regions, there are 20 possible pairs, okay? And for each pair, you simply do a sum of the regions to calculate the number of students reached with each pair. And then the question becomes, where do we locate a sales representative? In which pair? All right? And our objective is to maximize the total number of students reached. Okay? So in terms of constraints, we have down the left-hand side, we have our 11 regions. Okay? And so for region 1, any pair that has a 1 in it gets a 1 down here in the constraint. Any pair that has a 2 in it gets a 2 here, and so on. And so as you can see, you build the You build the conflict model by doing this. All right. Now the capacity is no more than we tally up at the bottom here. We have a capacity constraint. We have 3 sales representatives. So in other words, we can only choose 3 different pairs to maximize the number of students because we only have 3 sales representatives. All right, so that's why we have this constraint at the bottom. Okay, everything else is a less than or equal to 1. Okay, because remember that these can't overlap. So, for example, we cannot have a sales representative in more than one of these three pairings. Okay, because then you'd have too many sales representatives. They would overlap, and that is one of our constraints. We don't want them to overlap. Okay, so again, think this through and work backwards from this solution if you have to, but this is how we do a set packing problem. Set partitioning is sometimes known as matching, all right? And it's actually similar to the assignment model, okay? And what we do is we match pairs within the same population rather than different populations, such as cars and factories. Okay, in the assignment model that we did a chapter or two ago, we matched cars with factories. All right, but in this particular case, we are going to match pairs of things, whatever they are, within the same population. All right, and the goal is to minimize the number of conflicts. So each constraint column represents a set that is in potential conflict, and the sets must be partitioned to minimize conflict, and that's why it's known as partitioning. So let's get into it. This happens all the time in academia. So we have Oxbridge College. It has 8 courses and 4 final exam periods. All right. Each course must have an exam period. So the conflict array shows the number of students with conflicts between 2 courses. All right, and so this is data that you will have gotten from SAS or from from your student administrative services, the registrar, that kind of thing. All right, so for example, between time T1 and T2, there are 20 conflicts. All right, so what we need to do is we have to choose the 4 periods with the least total conflict. It is inevitable that you're going to have a student that has final exams that are both scheduled in the same time period. Okay, this just happens. So and you have to make accommodation for it. But obviously, making an accommodation is a pain in the neck. So what you try to do is minimize the number of periods that have conflicts so that you have to do the least amount of accommodation. So here is the spreadsheet model. Okay, once again, you can see at the top that we have paired things up. All right, we've paired up the different time periods, 1 through 7. Okay, and we have listed below that the number of conflicts. So we've basically taken that data that was in the previous slide and put it into linear format, linear model format. And so the question is what time periods do we choose to minimize the number of conflicts that we have? So for course 1, for example, look at the bottom here. Course 1, anything that uses time period 1 has a 1 in it. Okay. For course 2, anything that has a 2 gets a 1 in it. Any of these pairs. Okay. Once you get the pattern for doing this, it actually becomes quite easy. For course 4 down here, any of those pairs that has a 4 in it gets a 1 in the constraint field. All right. And so since there can only be one time period that a course has an exam, all right, then the right hand side and the left hand side is essentially a balance equation. They both have to equal 1. All right. Now I know this can be confusing, okay, but think it through. All right, and you'll see what is happening here. You're choosing the time periods that will give you the least amount of conflict. You've essentially got to you've got to have conflicts. All right, so you're choosing the 3 pairs that give you the least amount of conflict. So, for example, we've chosen 1 and 5 to overlap, 2 and 6 to overlap, and 3 and 8, and 4 and 7. Those are our 4 time periods, right? Those are our 4 time periods. So we've chosen which courses are going to overlap, that result in the least number of students, in this case 76, having conflicts. So let's take a look at another example of integer programming, and that's a playoff schedule for soccer playoffs. There are 6 teams, 2 divisions, 3 from each division, and each team must play every other team. All right, each team must play once a week. Therefore, the schedule will require 5 weeks of playoffs. The objective is to maximize the intra-division games later in the schedule. So it's really kind of a 2-part objective. And now, this is a complex model, probably not something I would ask on an exam. All right, and this is actually only the partial spreadsheet model because it won't really fit on one slide. Okay, but as you can see, we've listed out the potential team matchups for each week. All right, and so each team has to play every other team. Each team has to play once a week. All right, so those are constraints, and we want to maximize the number of teams that are playing later, the number of intra-division. Okay, teams playing later on in the schedule. All right, go to the chapter spreadsheet to see the full model. So let's take a look at how Solver solves an integer problem, and it uses a technique known as branch and bound. Okay, so when integer constraints are added to a model, Solver works differently. And as I said, really requiring an integer is technically a violation of the rules for linearity. Okay, but Solver works around this with the branch and bound procedure. So if a model solution contains non-integers, Solver uses additional constraints to split the problem into 2 different problems. It creates a branch. All right. Non-optimal solutions are discarded, and this is what's known as the bounding process. And so the process continues until an optimal integer solution is found. Okay, so actually, Solver is using multiple linear programs, and so the power of the linear engine, the simplex engine, is retained, and a global optimum is guaranteed. Okay, so although by requiring integers we are strictly violating the rules of linearity, Solver uses multiple linear programs to find an integer solution. The book actually goes into a little bit more detail about branch and bound, so look that over. It's not really something that I want you to spend a lot of time on. Okay, just understand that there is a reason why we can violate the rules seemingly and still use the linear engine. And really, the linear engine is the key here. It's one of the reasons we spend so much time on linear programming and not so much time on nonlinear programming, because the linear programming engine is the most powerful. Linear programs are the most powerful. Okay? So, in summary, integer models look very much like the standard linear programs that we have had, with some integer constraints added. But we also added a second type of integer model where the decision variables are binary, 0 or 1. Okay, and there are three basic types: set covering, set packing, and set partitioning. And as I said, go back and look those over. Look at the spreadsheet, the chapter spreadsheet, and make sure you understand these. Okay, and then lastly, although integer constraints violate the rules for linear programs, Solver uses a procedure internally to solve the problem using the linear engine, which is really our goal because the linear engine is the best one that we have. That's it, and we will check back in with Chapter 7.